All right, so this is Physics 1C for October 6th, the first hour. Tonight we're going to be talking about magnetism. We're also going to finish some things about RC circuits that we discussed last time, but primarily we're going to be talking about magnetism, and that's going to include kind of the origins of magnetism as it was discovered here on Earth, as well as the magnetic field of the Earth itself. We're going to talk about magnetic poles, how they attract and repel each other, like north and south poles that you're probably familiar with, monopoles. We'll then go into talking about magnetic force. In particular, what we're going to learn is that magnetic force is something that we're going to describe in terms of charged particles. And then we'll talk about magnetic flux. And then my guess is we'll probably get to about here and finish the rest of the stuff on Thursday. But we'll talk about the motion of a charged particle in a magnetic field. The idea that you can kind of bottle up electric charges by using a magnetic field. And then later on, we'll talk about things like mass spectrometers and electric motors and how they work. So a lot of really interesting stuff in this chapter. I believe this is chapter 29, 27. This is chapter 27. It's a pretty thick chapter in terms of what's covered. And because it's magnetism, I hope that you find it interesting. Magnetism is a very interesting force, and we can do a lot of really neat things with it. And I've got some demos via videos to show you in regards to that. So to get started, though, we're going to finish up something we did last time. At the end of last class, we were talking about a RC circuit. Just to give you an idea of what that was, as it's been a few days. An RC circuit is where you have a connection of an R, which is a resistor, connected to a capacitor, C. And then you have it connected up to some type of EMF source, and it could be a battery, it could be anything like that. And you usually have some kind of a switch. And then we say, what happens if we close the switch at time equal to 0? And we went through a derivation where we showed that charge on the capacitor, Q, as a function of time, was equal to, what was it? C, the capacitance, multiplied by the EMF, and then multiplied by 1 minus e to the negative t divided by r times c. And that tells you the charge on the capacitor is a function of time. At time equal to 0, the charge starts off at 0 because this term is 1, and 1 minus 1 is 0. And then as time goes on, the charge grows on the capacitor, such that if we wanted to plot what it looks like, and we were to plot on the y-axis the charge, and on the x-axis time, then the charge is a function of time as a thing that looks kind of like this. It asymptotically approaches a maximum charge, and the maximum charge is given by that. Q max is equal to the capacitance multiplied by the EMF. And we want to use this idea to describe how to solve this problem right here. And one other thing to add was that there's a time constant that we define for the circuit that's called the RC time constant, and often the symbol tau is used. And it's equal to the resistance multiplied by the capacitance. And what we learned is that this is the time that it takes. So this would be right here, t equal to tau. For the charge on the capacitor, or the voltage across the capacitor, to reach about 0.63, not much room to write in here. I'm really trying to bunch up a lot of stuff. At this point, the charge is about 0.63 of the maximum charge. 63% of maximum charge. So what is the time constant? It just gives you some idea about how long it takes to charge up. Okay, so here's a problem that we could do with this. We have a 10 mega ohm resistor that's connected in series with a 1 microfarad capacitor, like this here. So let's write down what we have. The resistance is 10 mega ohms. That's 10 times 10 to the 6th. Not 10 to the 6th, but 10, so it's really 10 to the 7th ohms. That's the resistance. It's connected with a capacitor, where the capacitor has a capacitance of 1 microfarad, so that's 1 times 10 to the negative 6 farads. And it's connected to a battery with an EMF of 12. So all of this is consistent with the picture that's drawn up here. The battery has an EMF of 12 volts. Before the switch is closed at time equal to 0, so this is usually how this is done, is that the switch is closed at t equal to 0. The capacitor starts off uncharged. We want to find what is the time constant, and then what fraction of the final charge is on the capacitor at this time, and then what fraction of the initial current is still flowing at this time. Anyone have any questions about this? All right. So the first thing we want to do here is what is the time constant? Well, that's this thing right here. We just do tau, time constant, is equal to the resistance times the capacitance. The resistance is what you can see right there. And the capacitance is right there. Pretty easy calculation to do there. You're going to get, the 10 to the 6's cancel out. You're going to get 10 seconds. 10 seconds. That is the time it would take for the capacitor to charge up to about 63% of the charge max. One thing I guess that's probably worth looking at here is the units and making sure they make some kind of a sense. So what's an ohm? I'm going to write down a couple equations here to remind us what those things are. So to get ohms, we know that delta V is equal to I times R, right? So you can divide the I over here to say that for the units of this right here, you've got ohm is going to be volts over amps. And we're multiplying that by a farad. Farad comes from this piece right here, so it's a coulomb divided by a joule. Resistance is volt over amp. Coulomb over joule. Okay. This is going to work out. A volt is a joule per coulomb. Wait a second. A farad is coulombs divided by joules. Yeah, looks right. Okay. Volts is joule per coulomb. Amp is a coulomb per second. Something's wrong here. So this is the ohm. We're multiplying by the farad. Yeah, there's like one too many coulombs, isn't there? Why do I think this is supposed to be coulombs squared? Let me think for a second. I know what I did wrong. I know what I did wrong. Okay. Yeah. Much easier than what I've done here. So an ohm is definitely a volt divided by an amp, but according to this equation up here, to find out what C would be, the capacitance C, which is farads, it's coulombs, it's coulombs divided by volts. EMF has values of volts. This should have been coulombs over volts right here. Sorry about that. So it's coulombs over volts. Then it works out, because then it's volts, those cancel, and you get seconds. Sorry about that. Okay, so that's the answer to the first part. 10 seconds. Any questions about that? Or questions in general about RC circuits before we continue? Okay. Part B. So the next thing we want to do is to figure out what fraction of the final charge QF is on the capacitor at t equal to 46 seconds. Okay. When it says final charge, another word for that would be what I'm calling maximum charge right here. Okay. So for this, we're going to need to look at our equation, which says that the charge as a function of time is, so C times E, we could rename this. CE is just the max charge. And we want to find what fraction of the what fraction of the final charge is on the capacitor at that time. So we need to know what the charge at 46 seconds is. So since it's a function, we'll just write Q of 46 seconds. And we're going to divide that by the maximum charge here, Q max. And this ends up being equal to 1 minus e to the negative 46 seconds divided by r times c. Maybe now it becomes clear why you care about finding this. It shows up in your equation. So r times c we just found was equal to 10 seconds right here. So that right there should be the fraction of what there is, right? Because it's the charge at that moment in time divided by Q max. So this quantity here will give us the fraction. So it's going to be 1 minus e to the negative 4.6. So what's that equal to? Wait, that looks really bad. What is that quantity equal to there? It's 1 minus e to the negative 4.6. Yeah. Really, really close to 99%, right? So that's 98995, I think. We could just put 0.99, but there you go. So about 99%. This goes to show you that after about four and a half time constants, you're pretty much at full charge. And I believe we kind of saw this from an air quote demo that we did last time. Any questions? Okay, part C says, what fraction of the initial current is flowing at this time? So this gets into something that we didn't actually look at last time, but I think I mentioned toward the end of class. So if I know that the charge as a function of time is equal to this, how could I find the current as a function of time? Take the derivative, yeah. So the derivative of this expression right here, the derivative of the first term is going to be 0, right? You can take the derivative yourself for this, see what you get. I believe what you're going to get is something like that, which we can simplify because Q max was equal to C times E. Which means that the current as a function of time ends up being equal to, the C's cancel, just E over R times e to the negative T over RC. The question was, what fraction of the initial current I naught is still flowing at t equal to 46 seconds? The initial current I naught, what would that be? That's like the current at time equal to 0. What would that be in this equation right here? If I plug in 0 for time, what's the current going to be? What happens? What's the value that I get here? Don't worry about the numbers. Just what is it in terms of what's written here? E over R, yeah. Okay. So that is I naught, right? So what we can do is we can just kind of rewrite our equation that it's I of t is equal to I naught e to the negative T over RC. Oh, and it's the same question. What fraction of the initial current is still flowing? I can tell you it's almost certainly going to be 1%, just because it's going to be kind of the opposite of this here. So let's look. So if I plug in I of 46 seconds, you can even see it because of what we did right here, or sorry, what we did here, right? Divided by I naught is going to be equal to e to the negative 46 divided by 10. And we saw before that 1 minus e to the negative 4.6 was this, so this is going to end up being 1%. The reason why I put I naught in the front was because from this here, I naught is defined as the current at time equal to 0 seconds. If I plug a 0 into here, it's e to the 0, so you get e over r. That means that I of 0, which is also called I naught often, is just e over r. So I just replaced e over r with I naught. Okay. Pretty easy problem. I don't know that we need to do this one. I do want to kind of get through things, and this is going to be really repetitive. Is it that resistor and capacitor connected? The capacitor initially has a charge of 5 microns. It's discharged. At what time will the charge be? This is okay. It's a little bit different, so let's do it. So this is discharging a capacitor. The difference here is that there's no battery. There's no battery in this case. All you have is just a capacitor. It's the same capacitor and resistor from the previous problem. The difference being that the capacitor starts off charged. So you start off with an initial charge, Q of 0. It's equal to, what is it, 5 microcoulombs. And we're going to close the switch. And then what's going to happen is that this charge that's on this capacitor, let's say this is the positive side and this is the negative side, it's going to cause a current to flow in the system, like this, an instantaneous current. Now you're right, Tyler. That's always going to be true. Yeah, if you look at the relationship, since this one's given by 1 minus e to the negative TRC, and this one's given by e to the minus t over, and that this quantity is always a fraction, e to the negative t, this will always be a fraction. That's true, isn't it? Yeah, this is a number between 0 and 1, like guaranteed, right? Because even if t was infinity, you'd have 0, and if t is 0, you have 1, so this is always a fraction, so that will always be the case. The percentage that you have here, and they'll always add to 100%. Yep. Okay, so in this problem, it's a little bit different what's going on, because now you start off with the capacitor already having some charge, and you close the switch, which then makes this current flow. And what I'll tell you is, without deriving it, although you could derive it yourself or you can look in the textbook, that in this particular problem, what's going to happen is that the definitions of what the charge as a function of time is, the charge as a function of time in this case is going to just be the charge that you start with, Q naught, multiplied by e to the negative t over RC, and then the current, because now you want to start off at time equal to 0, you want to have the initial charge be this value here. And as time goes to infinity, you want the charge to drop to 0. And then with the current, you want something similar to have happen. But I think, again, we can basically just take the derivative here. The difference is we need a 1 minus t over RC here. Right? Because at t equal to 0... Oh, no, this works out, right? This works out. Yeah. The negative sign here just indicates what direction the current flows. But we really only need the first equation. That's the only one we're going to need. It says the capacitor has an initial charge of 5 microcoulombs and is discharged by closing the switch at t equal to 0. At what time will the charge be 0.5 microcoulombs? So what we know is that the charge at some time t that we're searching for is equal to 0.5 microcoulombs. We know that we have the values that we were given in the previous part, which is that the resistor is 10 times 10 to the 6th ohms. And we know that the capacitance is 1 times 10 to the negative 6 farads. There we go. Oh, we do need the current for the second part. At what time will the charge be equal to this, basically? So we're solving for time now, right? So looking at our equation right here, we would write Q at that time. Let's just go ahead and divide by Q naught. Should be equal to e to the negative t over RC. In this case, we're searching for time. We can plug in some values. The charge at that time we're given as 0.5 microcoulombs. The initial charge on the capacitor was 5 microcoulombs. And this should be equal to e to the negative t divided by 10 seconds, because the RC, when we multiplied it before, R times C, what we started with here, we got was 10 seconds. So we just need to solve this. What do we need to do to solve this equation? Oh, whoops. Take a lateral log, that's right. So we'll take a natural log of both sides. We take the natural log of this side, take the natural log of this side. On the right-hand side, we're going to get natural log of this. We'll kind of annihilate the e, and you'll have negative t divided by 10 seconds, and that's going to be equal to the natural log. Let's see, 0.5 over 5 is 5 over 50 is a tenth, right? So it's 0.1. We multiply the 10 to the side right here, and we end up getting that negative 10 seconds times the natural log of 0.1 should be equal to the time. And then we can solve that. I can't do that one in my head. If it was log, we could do it, because then it would just be... Anyway. What's that equal to? You're right, Jose, but then... Yeah, it could be 10 to the negative 1. We could pull the negative 1 power down in front of it, then we're doing the log of 10. But it's like, I don't know what the log of 10 is either. Maybe some of you know what the log of 10 is. I should know what the log of 10 is, actually, because that would help me for doing stuff like this. Okay. Time equal to 23 seconds. That's the answer. What is the current at this time? Well, for this, we just apply this equation here. And we say, okay, well, if I plug in the time, we're going to get the time, or the current at 23 seconds is going to be equal to negative Q naught was 5 microcoulombs. That was given in the problem. R times C, 10 seconds, multiplied by E to the negative 23 seconds divided by 10 seconds. So it's going to be something like, this is going to give us an answer in microamps. What's that equal to? .5 microcoulombs per second, right? Is that what you get? E to the 2.3 you end up getting, you guys agree with that? Wait. This by itself is 0.5. That can't be the right answer, is it? Unless this is 1. Maybe it is 1. No, it can't be 1. Maybe it could. No. There's no way. What? Wait. Okay. That's the charge. Sorry, we're trying to find current now. Oh, were you saying the one in the numerator should have been 5 microcoulombs? I get it now. That is correct. That is definitely correct. Because it's... No. Okay. I'm not being clear. Q naught, right? In this equation, Q naught, that is 5 microcoulombs. The number that shows up right there is 5 microcoulombs. So that is correct. 0.5 was the charge at this time. But this equation uses the charge initially. Do you understand now, Mr. Miars? I think so. Okay. Fair enough. As long as kind of close. You get 0.05, Anna? Okay. I believe you. I'm just putting this in because it took a while. Nobody else answered, so just to verify. Yeah. I agree. 0.05. Okay, so 0.05 microamps. And that's going to be the current at that moment in time. And there was a negative sign here, so I should include that, I guess, but it really just tells us direction when we're talking about current. I of t. That's the current at 23 seconds. Okay. So why do the Q of t equations differ from the other question? Good question. In this problem, the situation was that the capacitor was initially uncharged. And we closed the switch, and then the EMF here drove charges onto it until it became charged. In this problem, it's discharging a capacitor, so we have to use a different equation. And this equation is derived in your textbook. I could derive it for you too, but I don't think it's going to be useful. It's going to be very similar to the derivation we used previously. Yep, you got it. Good. Okay. Any other questions? Okay, let's talk about magnetism. It's complete, total change. Oh, I will say, one thing I want to encourage you all to look at, and maybe we'll just briefly talk about it. There is a section in your book on fuses and circuit breakers. And it's right at the end of this DC circuit section. It's called Household Wiring and Safety. If any of you are looking into becoming electrical engineers, or if you're just looking into like learning something about wiring a home, this segment is pretty interesting. Oh, wrong book. Whoops. All right, so it's the last section of chapter 26, right here. Power distribution system. Sorry, that's what it's called. Excuse me. So, in this section, what they kind of talk about is how your home has kind of wired. How within your home you have these things that are called fuses. I'll answer your question in a second, Ash. Within your home, you have these things called fuses and a power meter that gauges exactly how much you use. It shows kind of like how all the outlets are wired in parallel. Can you see that? Like, there's a lot of stuff on this picture. So this is something... Oh, yeah, you should read all of it, Anna. Yes, definitely. Do people read all of it? Absolutely not. I'm sure a lot of people don't have time. It's good that you do. When I took this class, I definitely read as much of the chapters as I could, and I read it multiple times. I do not expect anybody else to do that. But if you really want to learn about this stuff, like we said at the beginning of class, it's on you. You want to... Yeah. But some of the things that are described in this picture are this idea of ground, which is... The ground is quite literally a piece of wire that's connected to your circuit that runs into the ground, and it allows you to take and receive excess charges within the system. It's a safety device that's used to help you from getting electrocuted. One of the things that's discussed here is the idea that your house can only sustain or have so much current flowing through the system before the wires themselves can start to burn up. So there's safety devices. Two examples of those safety devices are called fuses, which is this right here, and a circuit breaker, which is this right here. Most of your homes these days are probably wired with circuit breakers. You may have cars that still have fuses in them. I know a lot of the electrical equipment that we use at the school has fuses in it, so that are designed to like make sure things don't have too much current flowing through them. A fuse is basically described right here. A fuse basically contains a tiny little link right here of a lead tin alloy with a very low melting temperature. Whenever too much current flows through this, the wire literally burns and breaks. And when it happens, you see like brown and gray and black smoke that will kind of show up inside of here and stain the outside of it, giving you an idea that the fuse is broken. And when that's happened, it makes it so that you no longer can get current flowing through your house. So this is designed to, make sure that the wires in your house don't break. The circuit breaker is a similar idea. On the circuit breaker, what happens, and this is probably something you could see if you look around your house enough, the switch on the circuit breaker will flip if the maximum allowable current is exceeded. And basically what happens is it just cuts off all the power on that section of your house, and if you want to get the power flowing again, you can turn it back on. This is something that can happen if you just let too much current flow through. And when does that happen? That would happen if you just have too many devices all running at once. Like if you're washing your clothes while you're running the microwave and listening to a sound system, and you've got your refrigerator running and it's hot outside, and you've also got the AC running. If you have all these different electrical devices that are all running in your home at once, it could overload the circuit, and then the breaker would trip, and then that would cut power to all your things in your house, and you'd have to go and flip the switch back over and try to use less things, basically. So anyway, definitely something worth talking about. It also describes the advantages of using a 3-prong plug with the ground compared to a 2-prong plug. And I just encourage you, be sure you actually read this if this is something that you're interested in knowing about. Okay? All right. So that is the end of that chapter. And what we're going to move on to talking about now is magnetism. So let's do that. It is 7 o'clock, so we would normally take a break here, but we didn't really start until like 6:30, so I'll probably go a little bit longer before we take a break. All right, what is magnetism? What do you guys know about magnetism? When do you think magnetism was first discovered? What do you know about it? The origins. When did we first learn about magnetism? What do y'all know about that? It's not really true. But there is this nature in which they can be perpendicular to each other in certain situations. But it's easy to set up a situation in which they're not. Now, what do you know about when magnetism was discovered? How long have we known about magnetism? Does anyone know about that? How long have we known about magnetism? 100 years? 200 years? Okay, you would assume a long time. Okay, why do you say that? Because it's fundamental? Okay, well, still have to find magnets, right? Okay, it's present in nature. Good point. How is it present in nature? Where can I go out and find a magnet in nature? Or where might someone have found it before? Maybe certain types of metals, maybe like iron, for example. Maybe iron from the earth might exhibit magnetic properties. What are magnetic properties? Magnets can do stuff like pick up little pieces of metal, right? You bring a magnet near some paper clips, the magnet can pick up the paper clips, right? And the paper clips will stick to them. You all probably have magnets in your house on your refrigerator. Maybe not, I don't know, but something that sticks to your refrigerator where you can put notes and it'll hold them up and do so for a long period of time. It does so without adhesive, right? If you want to put something on the wall, like a poster, you might need like nails or glue or some kind of sticky substance, but on your fridge, because your fridge is magnetic, you can put magnets on it, right? Okay. So magnetism's been known about for a really long time, and your book would have you believe that the first magnets were found about 2,500 years ago in ancient Greece. But that's really common in textbooks in the United States, and probably in, I don't know about Europe, but probably in Europe as well, where they always like to say that like a lot of our knowledge came from the ancient Greeks. In reality, Eurocentrism, Western centrism. In reality, the ancient Chinese civilizations also had access to this stuff. Magnetism in China, I know, was connected to, at least for a while, people would use them to find what were called, I think, ley lines. They were looking, they thought they had magical powers and that they might, whatever. But pretty quickly, both the ancient Chinese and the ancient Greeks figured out that if you were to take these pieces, so what do they find? In Greece, they found things that they called, that we now call lodestones. Is that what they called them then? I don't know. A lodestone is basically a natural magnet. It's a naturally occurring magnet. And what they noticed is that these lodestones could pick up little tiny bits of iron. Certainly they had access to iron at this time in Greece as well as in China. And these lodestones would pick up these little tiny pieces of iron. We don't really know how they're produced, but they were found on an island in Greece called Magnesia. I think, is Magnesia the name of the island? Maybe I'm wrong about that. Maybe it was Magnos. I don't know. I have to go look that up. But maybe one of you can verify that. But that's why we call them magnets, I think, is because it was found on an island that had the letters M-A-G-N-E-T or something in them. I think it's Magnesia. Yeah, so these things, they could pick up little bits of metal and stuff like that. It is magnesia, okay. So how these things were formed, why they were magnetic, I don't know that we have an answer to that, and I think there's theories out there. Some people thought that they were like struck by lightning. It could be the case that they were aligned with the Earth's magnetic field, which is something else we'll talk about now. But somehow these things actually occur in nature. You can actually go out and find these things. I don't know how easily you or I could go out and find a magnet in nature, because nowadays it's much easier to go to a store and buy a commercially manufactured magnet, right? Regardless, they found these things, and this was a very long time ago, right? One of the ways in which they started using these things, though, is how do you make a magnet is something we will talk about next time. Oh, there was a question that I didn't answer. Ash, sorry, I want to get to this part. I forget. You said, What's the difference between this class and an electrical one? Someone asked that earlier, and I was curious about the answer. Oh, so I missed the other person's question too. My bad. Like the difference between this and an electrical and engineering course, I would say is probably an electrical engineering course would focus more on. When you say electrical one, I don't know. Yeah, not that person asked Cronius, but I wasn't there. I've never taken an electrical engineering course. I know that there are a lot of different electrical engineering courses. There's not like one. Like there might be some schools where you have like an intro to electrical engineering, but electrical engineering is broken down into multiple parts. So I know like you take 2 courses in circuits, for example, in which you have to memorize the resistor codings. That's really not that hard, but you have to memorize how to read them probably. I don't know if you memorize the codings themselves, Miars, but it's really not that hard. I had my other class do that when I taught at a different school. I thought it was kind of fun. Yeah, it can be a little intimidating. I agree with that. Just like any type of code, but once you understand the code, it becomes pretty simple because it's just a color, represents a number, and it uses base 10. So there's multiple electrical engineering courses. That's what I would say, Ash. It's broken up into a bunch of different parts. So you could have I think there's 2 semesters on circuits that you take, and then there's going to be other courses too. And I don't, off the top of my head, I don't know, but you could go look at a electrical engineering department. You could look at the courses they offer, and you'd see it's the simplest way I could say it is that it's just a lot more detail, and you learn a lot more strategies for analyzing things. When it comes to circuits, we learned about Kirchhoff's laws, right? The loop rule and the junction rule. It turns out that there's a whole bunch of other different rules for circuits where you can do these reductions, and those are some of the kind of things that you would learn in those classes, as well as you would learn about like actual applications of these things as opposed to the theory behind like what it is. Like in physics, we're teaching you what are the principles behind which charges start to move in a circuit, and then we define this thing called current, right? So we started off with defining the electric fields, and then we learned about potential differences, and then we said battery has potential difference, put it in a circuit, it creates an electric field. Okay, so now what we want you to gain out of this class is to understand why do the charges move the way they do. What is the fundamental reason why these things are moving? Ultimately, at the end of the course, the other things that we'd like for you to be able to describe is how do you make a magnet? Someone said that just now. We're going to answer that question, Miars, in the next chapter about how you actually make a magnet. Okay, that's something else that we want you to understand is like how would you make a magnet? How could you make it stronger? And then in addition to that, we want you to understand like at the core how a motor works, how a generator works, as well as how AC circuits work and all that kind of stuff. So this class is all physics classes, especially these introductory physics classes, they're all about general principles behind which these things work. And then when you go take an electrical engineering course, you're going to just take it to the next level, and you're going to look at applications and stuff like that. We learn how to Yeah, we'll talk about how to demagnetize magnets. I can answer that question very simply. You heat them up, or you strike them against. You need to cause random motions of the molecules. So it's you either heat the magnet up beyond a certain temperature, at which point the temperature fluctuations will cause what are called the magnetic dipoles inside of the object to rearrange themselves. So maybe that's something we'll address later, because I realize you need to understand maybe a little bit about what a magnet really is to know that. But okay, all right. But that is basically it. You just heat it up. If you heat the magnet up to a hot enough temperature, then you can demagnetize it. That's the simplest way to put it. If you have a weak magnet, such as a magnet that you've produced by like wrapping a wire around a nail, and that nail has now become magnetized, you can actually demagnetize something like that if it's a weak magnet by just taking the nail and just banging it on a surface. Like, so you could take the nail and you could just bang it on a table, and with enough like fluctuations within the material due to the vibrations, you could actually demagnetize it as well. Yeah. Okay, so let's get back to, you're just typing something, Jesus, and I'll read it, but I'm going to keep going here. So these lodestones, these natural magnets, one of the first kind of applications people found for them was that if you took one of these lodestones and you kind of put it into a bowl of water and you let it float, they found that the lodestone happened to actually always point with one end of it kind of toward the northern direction. Okay, basically the idea of what was now often referred to as a compass. So a compass is basically just the idea that you take a magnet and you let it float freely and you just see where it points. And what'll tend to happen with the compass A modern compass looks maybe something like this, where you've got two sides to the compass, and one side is often painted red, one side's often painted white or black, and it's kind of in a floating. It's floating in like a liquid or something like that, so it can kind of move without too much resistance. And what these ancient astronomers and people that were navigating in the oceans figured out was this was a really nice way to know what direction north was, because these magnets always tended to point north, and that led them to believe that the Earth itself must have some magnetic properties. And I'm sure many of you know that the Earth has its own magnetic field. Now, I'm going to show you guys some pictures of things that I've pulled in here, so that we can talk about this, such as this right here. This is a picture of iron filings, and I want to grab the picture of the Earth too. Here we go. Here we go. We want that one too, don't we? Yeah, we'll come back for that one. We'll do that one last. Okay, so let's talk about magnets themselves and more modern understanding of a magnet. So here's some examples of some magnets here, okay? And what's shown is what's called the magnetic field, okay? These are bar magnets that are probably something you're familiar with. Oh, there's some questions here. Are those Van Allen belts? It's related to that, yeah. So, the Van Allen belts are more related to charged particles, but I think we'll talk a little bit about those a little bit later, though, so we'll come back to that. Okay, so this is an example of different magnets here. And I guess I should say something very simple first, which is to say that one thing we can say about magnets is that they're always going to have a north pole and a south pole. And let's just start off with the basics. If I take the north pole of a magnet and I place it near the north pole of another magnet, y'all know what's going to happen, right? Or what's going to be felt here, right? There's going to be a force between these two. Is it going to be repulsive or attractive? If I put two north ends of a magnet next to each other, yeah, that's right. So there's a force that goes this way. There's a force that goes with it this way. Okay. Alternatively, if we take a magnet and we put the north end of the magnet here, we put the south end of the magnet here, then there's now going to be an attractive force. And in general, what we can say is that, so this is a attractive force. These two would be attracted to each other. And if I place these two near each other, chances are they would kind of snap together. If we put these two together, then they're going to kind of just be pushed away from each other. Is this related to Coulomb's law? Coulomb's law is the law that describes how electrically charged particles interact with each other. It is not connected to magnetism, no. The strength of the force in this case, it is related to the distance between these two, though. So the closer together the north poles get, the stronger the force becomes. The farther apart they get, the weaker the force becomes. I believe that... I'll probably be wrong about this. The force between these two, I believe, varies as either 1 over x cubed or 1 over x to the 4th power if you define the distance between them to be x. It's 1 over x cubed or 1 over the x to the 4th. I don't really remember what it is. But it's often not something we talk about a lot, specifically in this class, because we learn other things about magnets. Regardless, it's not related to Coulomb's law, no. All right, so what else to say about magnets in general? So these magnets, what we can do is we can use the idea of... Whoa, how did that even pop in there? That was weird. What we could do is these magnets have the property that they will attract little bits of iron. And what's displayed here are basically magnetic fields. On the left side, you have the magnetic field of just a single bar magnet. And the way this is produced is you sprinkle little pieces of iron all over the table, and the iron will basically kind of line up in the direction of the magnetic field. It's kind of similar to the compass. If you could imagine taking this compass... Oh, does it go behind here? If you could imagine taking this compass and putting it, let's say, like at this location here, the compass needle would point... This is north, right? The compass needle at this location... Let me get a red. See if that shows up there. If I put a compass at this location, it would point that way. If I put a compass at this location, it would point this way. Put a compass here, it would point this way. Basically, tangent to the way these all are. That's what the compass would do. Okay? And the filings are a type of thing that we can actually see the magnetic field. And that's kind of nice. Being able to see the magnetic field is kind of powerful. It has a lot of similarities with an electric field, specifically for the electric field of what? What kind of electric field would this look like? Or does this look like? The electric field for what? A dipole, yeah. Where you'd have like a positive charge and you have a negative charge over here. So they're really similar in that regard. The fields that are produced by these, we call this a dipole magnet or a bar magnet. Okay. This would be the field for a dipole as well, where this is the north side and this is the south side. And this is a north-north, which is what it looks like when you put a positive charge and a positive charge in terms of fields. So luckily, with our experience with fields, the idea of a magnetic field, I hope, isn't too foreign to you. The magnetic field itself, unfortunately, we can't describe it as simply as we can the electric field. So if you remember, electric field we could describe by just saying, oh, well, it's just equal to, the force placed on a particle divided by the charge, right? And we talked about what this was for all kinds of different arrangements, but in general, the field was basically just, if you were to place a charged particle at the location, there's going to be a force that's felt. In this case, it's not so simple. We'll talk about this. There's no such thing as a magnetic charge, so you have to have the effect of like a dipole, i.e. a compass being placed in here, or pieces of metal to actually see the magnetic field. Okay. Okay, any other questions as I'm moving on? Let's make this a little bit smaller. Okay, I mentioned that people used these natural magnets to produce compasses, and the reason why these compasses were able to find the northern direction is basically shown a little bit by this picture right here. So the Earth itself has a magnetic field. The magnetic field of the Earth is a very interesting and complex thing. What's shown in this picture here is not meant to be 100% accurate, but some of the features are. The magnetic field of the Earth is very similar to the magnetic field of a bar magnet. What we call the North Pole of the Earth, the northern geographic pole, is actually the southern magnetic pole. Does that make sense? If I tell you that compasses always point north, and I tell you that for the compass that this is the North Pole and this is the South Pole of the compass, does it make sense that the South Pole of the South magnetic pole of the Earth should actually be at the northern geographic pole? Does that make sense? The compass is always going to point north geographically, but it's attracted to the southern pole of the Earth, and the compass needle would always kind of line up like this. That's the direction that the compass needle would line up if we thought of it as just an arrow. So if I'm sitting right here in Los Angeles and I get a compass out, it's going to point off in that direction. Now, it won't point flat on the Earth, though, right? It's actually going to point slightly downwards. It kind of points into the Earth, because it has to point, towards the magnetic pole. The actual north geographic pole of the Earth and the magnetic south pole, they're not aligned with each other either. There's actually a slight variation. In this picture, it's 11 degrees. And this is something that actually changes over time. It kind of drifts. But nonetheless, it still generally tells you what direction north is. And if you know something about the properties of the magnetic field at your location, you can use it very well to orient yourself and navigate around. If you go get a map and you want to go hiking in the woods, for example, at like a national park, written on the map itself will be little pieces of information about the magnetic field at your location, including things like what's called magnetic declination. The northern lights are a result of the magnetic field at the North Pole. They are. We'll talk about that a little later. Yeah, like for a national park map. So if you want to use a compass and you want to really accurately navigate around, you need to know something about what's called the magnetic declination at that location, which is related to I'm not making this wrong, but like how much the magnetic needle dips below. But there's enough information on the map that you can use it to really accurately navigate around. Yeah. Have you seen those things on a national park map, Miars? Have you gone like hiking before? Where have you seen that? Is anyone here in Boy Scouts? You want to get the Orienteering merit badge? All right. Just a okay. Yeah. I could pull up a map, I guess, and we can talk about that, but it doesn't seem like a lot of people have experience with it, and I'm not trying to spend too much time if you don't on that idea. Okay, magnetism. General features are the idea that magnets can either attract or repel each other. They tend to always have poles. Compasses are a tiny little magnet that's designed to line up with the Earth, although the compass doesn't work very well if you have a magnet nearby, because the magnetic field of the Earth is really weak. This is what this piece right here is kind of described to show you. So here's some approximate magnetic field magnitudes. The unit for the magnetic field is the Tesla. It's named after a very famous scientist who did a lot of work with magnetism and electricity, and for whom there's lots of movies that have been made in recent years. These are different values of magnetic fields. The magnetic field at the surface of the Earth is very, very weak. There's even magnetic fields inside of your brain that are very weak as well. Very weak. But here's the magnetic fields at the surface of the Earth. It's 0.5 times 10 to the negative 4. A strong conventional laboratory magnet, so this is going to be a little bit stronger than the magnets on your fridge, but not much. You can see that it's, 4 orders of magnitude stronger? Right? 10 to the negative 4 and 2. So if you have a compass, it's really only going to point north as long as there's not other strong magnets that are nearby. Because if there's other strong magnets that are nearby, the compass needle is going to point towards them. Medical MRI units have magnets inside of them. Superconducting laboratory magnet is something that's used. We use these at the job that I used to work at a national laboratory. We had big magnets like these that were designed to cause charged particles to move in circular patterns. We'll talk about that a little bit later. But magnetic field of the Earth's really weak. Yeah, it's weak, but it's 100 times as strong as the Earth, right? So, I don't know what else to say about the magnetic field of the sun. I mean, it has a magnetic field. Most planets and stars do, I believe. I think that's true. Yeah, but it looks like the magnetic field at the surface of the sun is about as strong as the magnetic field of a bar magnet, so take that for what you will. Does anyone know what actually creates... It's okay, it is kind of trippy to think that the bar magnet's stronger than the magnetic field of the sun, but the thing about the sun is that the magnetic field is very uniform over a much larger region. Does that make sense? Like, so take a bar magnet, okay, you understand, but like, this bar magnet may be stronger than the magnetic field of the Earth. However, you wouldn't feel the effect of... So this bar magnet is presumably somewhere, right? So this is... You might have a bar magnet from some toys you have. There's some bar magnets at school. You're not going to detect those bar magnets at your house, right? But you can detect the magnetic field of the Earth at your house. So it might be small, but it covers a big range, I guess, is what I'm trying to say. Okay. Do I want to talk? Okay, well, let me make sure that I'm not missing anything out here. I think there was one other thing I wanted to talk about before we start getting into the math. Oh, here we go. So this is something that's really interesting. So presumably, at some point in time in the 1800s, a guy named Ørsted. Is this the first person to realize this? I don't know. It's the first person in the West, and it's the person that is kind of documented with figuring this out. So in about 1820, I believe, I may be getting the date slightly wrong, but sometime around 1820, not that long ago, 200 years ago, actually, Ørsted was in class. He was teaching a class, and supposedly he had this setup where he was doing something really simple. He had a wire, and connected to the wire was a resistor, and maybe some other things as well. Maybe the resistor was actually just a light bulb, because after all, resistors, a light bulb is just an example of resistors. So maybe you've got like a light bulb here, let's say, and a switch, and then an EMF source, positive, negative, like this. And you close the switch. What happens? The light comes on, right? That's not very impressive for you guys, I hope. You know that if you have a battery, you connect it up to a light bulb, you can turn the light bulb on, right? That wasn't the interesting part. The interesting part was that he happened to have nearby a magnet, so we'll just copy our magnet or this right here. He happened to have, oops, there we go. He happened to have nearby a compass. Now, I don't know how this compass was oriented or something, anything like that, but he noticed that when he turned the switch on, let's see if I can get it right so I can actually tell you which way it would point. In this case, if he threw the switch, he found that just very, very briefly, what would happen is that the compass needle would deflect down like this, and then it would go back. So when he threw the switch, oh no, it wouldn't go back. When he threw the switch, the compass needle would basically just go down and kind of start to align, maybe at kind of an angle like this. I don't know if you believe that's true or not, but supposedly he was sitting in a classroom. He was doing a demonstration for his students. He happened to have a compass just sitting nearby, and he realized that when he turned the electric current on, that the compass needle moved. And that was supposedly the first demonstration of the connection between electricity and magnetism. The idea that the two... Oh, no, I think I lost my little thing. I might just go to the textbook so I can show you the picture. Or I can draw my own picture, but I'm going to show you the picture from the textbook. It's this one, right? Okay. Just give me a moment, I'll get to it. There it is right here. So this is the picture I wanted to show you. So if you have a current carrying wire, like this one right here, so there's a wire, and I place a compass needle above it, then that compass needle is going to just point north, right? When the wire carries no current, the compass needle points north. If I have current flowing in this direction, the compass needle will be deflected to the right of north, or east of north. And if I have current flowing down in this direction, the compass needle will be deflected this way. And presumably this is something that Orsted figured out while he was giving a lecture, and I have a really hard time believing that. I think it's probably more likely that he figured it out and then showed it in a lecture, but regardless, that's the story we have today. So Orsted figured out that electrical currents I could say they can cause compass needles to deflect, but I'm just going to say produce magnetic fields. That's pretty groundbreaking. The idea that this concept of electricity, and electricity, to be clear, wasn't really developed until between the 1700s and the 1800s. Magnetism was a much older phenomenon. Magnetism had been known about it for 2,500 plus years or something like that. The ancient Greeks, ancient Chinese civilizations knew about magnetism. Magnetism is an old phenomenon. Electricity was a new phenomenon that was just being discovered around this time, and the idea that electricity and magnetism were related to each other was really groundbreaking. It's very, very surprising, I believe. And as we will see, the connection between electricity and magnetism has had a massive impact on your lives, whether you know it or not. Due to the fact that we use magnets to produce electricity on massive scales, and we use it to power our cities, and to power your homes, and to power every device you've ever used, really, because of this connection that was discovered back about 200 years ago. And if you think about it, I mean, I'm sure 200 years feels like a really long time for you if you're in your 20s, but in terms of the history of our civilization, it is a very blip of time of how long humans have been alive, and this discovery really ramped up our technological innovation and allowed the world to progress very quickly into what we now kind of refer to as the modern age of computing and quantum computing and all the new things that are coming about. And it kind of starts with this right here. So I think that's pretty cool. One last thing to say about this is that if you take a magnet, okay, let's say you've got a north-south magnet, right, bar magnet, right, and you get a saw or something, and you cut it in half, something interesting happens, which is that after you cut the magnet in half, you end up with a south pole on one side and a north pole on the other side here. And the other piece of the magnet does exactly the same, except this ends up being south and ends up being north. And then if you continue that process and you cut it in half again, the exact same thing happens again. You end up getting a south-north here. You end up getting another south-north here. South-north. Basically, every single time that you try to cut a magnet in half, you seem to always end up with a dipole. You always have two poles. You always have a north pole and you always have a south pole. And so it would be reasonable to ask, what happens if you keep doing this forever? And the answer is you never are able to completely isolate one of these poles. So the way we say that is that there's no magnetic charges. There's no analog in magnetism to charges. Right? In electricity, we have electrical charges, plus, minus, neutral, right? In magnetism, we have poles, north and south. However, those poles can never be isolated from one another. There's no magnetic charges. This is also sometimes the physics phrase is that there's no magnetic monopoles. There's no magnetic monopoles. There's no such thing as a pole that you can isolate by itself. Now, I am virtually certain that this is strong, like that this is true. But I'll say no with an asterisk because we currently have loads of scientists that are trying to find magnetic monopoles, and there've even been recent discoveries of systems that can exhibit magnetic monopoles. And maybe we'll watch a video on that. I don't really know, but as far as we know, magnetic charges cannot be isolated, and we'll learn more about why as we go through this course. More so in the next chapter, because we're going to learn that what Ørsted discovered, that electric currents produce magnetic fields, this turns out to be the fundamental cause of magnetism. Magnetism comes about due to electric currents of some kind, always. Whether those currents be the current flowing through a wire or little tiny currents that are occurring inside of atoms themselves, or wherever they're coming through, it's flow of charge, which is what current is, after all, that actually produces magnetic fields. And one thing you know about the flow of charge is that you can't have a flow unless you have a complete loop, right? You need to have a loop to have a flow of charge. And that's part of the reason why you can't have magnetic monopoles. We'll derive that in more detail in the next chapter when we actually look at the magnetic field produced by our loop of wire. But this is a pretty important problem in physics, is the absence of magnetic monopoles. And I say that because there are a lot of theories, and they are just theories, like theory in the most liberal use of the word, in which people try to describe the ways in which you can combine together gravity with electricity and magnetism. And out of these theories, often they require the existence of magnetic monopoles. So it would be a really big deal if someone could ever find an actual single magnetic monopole. A single north pole or a single south pole existing in isolation would have a massive impact on physics. That being said, it's being searched for forever. And will we find it? I don't know. A lot of theories predicted the existence of gravitational waves, and we didn't discover them until about, 8 years ago or something like that. I think 2012. Some theories that were produced in the 1960s predicted the existence of something called the Higgs boson, and we didn't discover that until about 8 years ago either. So, we'll see. The jury's still out on this one. But from a classical perspective, there is no need for magnetic monopoles, and magnetic monopoles will not show up in what's called Maxwell's equations. Okay? Do you all have any questions? What else do you know about magnets that I didn't talk about? What about your experience of magnetism? What do you know about magnets? What am I leaving out? This is all the math stuff, so we'll get to that next. But don't take metal devices with you into an MRI. Sure, because the metal will, yeah, it'll be affected by the very strong magnet inside of that MRI, which is pretty powerful. A magnet, an MRI basically uses magnets to. Yep, magnets can mess up computers as well. If you take a magnet and you bring it really close to a, okay, so it can do a lot of things, right? If you have a physical hard drive, not a solid-state hard drive, but if you have a physical hard drive that actually uses working parts, magnetism can heavily affect that hard drive. It can damage it. In addition, magnets can affect LCDs. If you've ever taken a magnet and, or not LCDs. You guys don't know about these. It's kind of old. Old CRT monitors would be heavily affected by magnets. Are LCD screens affected by magnets too? Yeah, that's right, Ash. But, okay, what kind of monitor was it? Was it one of those older monitors, the big, huge tube, like curved monitors with the glass on the front? CRT monitors are still used in Smash Melee gaming. It's good to hear, Nathan. That's good to hear. It could have been. I can't remember if it affects LCD monitors or not. I don't think it does. Your old chem teacher had a lab with magnets, and I guess that one of the students took it out of the plastic casing, released them, which caused them to collide and explode. Oh, they didn't explode, but they kind of broke. They shattered, yeah. So there's some really powerful magnets that you can buy that are called neodymium magnets. Magnetism creates spin in particles or electrons. It's related to that, Jesus, yeah. Yeah, there's these really powerful magnets we have at the school, Mr. Meowers, that have been broken in the same way. You learned about magnetic spin in chemistry. Yep. Was it magnetic spin? Oh, you learned about paramagnetism and diamagnetism. Okay, cool. Did you see any demos of paramagnetism, diamagnetism? So what he's talking about is there's three types of magnetism, kind of. There's ferromagnetism. The ferro stands for iron. So it's things that are made out of iron usually have these properties. So it's like nickel, iron, cobalt. Neodymium is another example. That's just your standard magnetism that we're kind of talking about here. But there's two other types that are a little kind of weirder. There's called paramagnetism and diamagnetism, and I get them mixed up sometimes. I believe diamagnetism is the one. Diamagnetism is the one that affects water, right? Is that right? The diamagnetism is the one that affects water. So we've got a really cool demo at the school where you can show that a magnet can actually attract a little bottle of water, which is really surprising. And it can also attract, like, crystals, too. So the big difference is that with paramagnetism and diamagnetism, that they are much, much weaker forms of magnetism. Yeah. Okay. Nathan, you're saying that an LCD monitor would be affected, but if the image changes, then the magnet can affect the monitor. Okay. Fair enough. Anyway, so magnets are very interesting. They're related to electricity. No magnetic monopoles. There's a magnet in the Earth, and we've known about magnets for a really long time. The cool thing we get to do now is we get to talk about the things that the ancients didn't know about, which are how can a magnet affect a charged particle? How can we produce magnetism? How can we control magnetism? What if we want to produce a magnet, but we want to make it really precise? We want to have a very specific value. How do we know that a superconducting magnet has this value of Teslas? You know, what is a Tesla, and where does it come from? So that's where we're going to go for the next couple weeks here in this class is to describe those properties. I think these chapters are pretty straightforward. I hope you think they're straightforward. You're going to need to review a little bit of like how the right-hand rule works to understand some of the stuff. But anyway, I'm going to go ahead and pause the recording right now.